Hello dear students, in this session let us continue some more theorems on simple function and let's move to further topics in Lebesgue integral. Okay, so this is one of the theorem on simple function. The statement says that let phi and xi be simple functions which vanish outside a set of finite measure. Then these two properties should hold, that is integral a phi plus b xi is equal to a into integral phi plus b into integral xi for all real numbers a and b. And one more is, if integral over phi is, this is not integral, if phi is greater than or equal to xi almost everywhere, then integral over phi is greater than or equal to integral over xi. These two things we have to prove. So first, what I have considered two sets in order to define two simple functions. Okay, so we know that the definition of simple function is phi of x is equal to integral over I is equal to 1 to n ai chi ei. Correct? So this is one point in my set. For this I have chosen one set, and for another function, that is xi, I have chosen one more set, that is ai and bj. These two are collection of points in the canonical representation of phi and xi. In your statement, they have given that these two simple functions vanishes outside a set. So from I is equal to 1 to n, all points will be inside my set. Outside means for I is equal to 0, that will be my set which is outside. Correct? So a0 and b0 vanishes outside the set where phi and xi vanishes outside these sets. Simple functions are vanishing outside the set. Correct? So phi and xi are vanishing outside the set, that is a0 and b0. Now I am considering your first property, that is integral over a phi plus b xi is equal to a into integral phi plus b into integral xi. So I can write a phi plus b xi as a as it is, and since I am defining phi as a simple function, so this is using definition of simple function alpha I into chi ai. This alpha I is one of the point in my set ai. Okay, similarly b as it is, this is from definition of simple function beta j is one of the point in my set bj, collection of set bj. Okay, so from one of the property of characteristic function, I can write this as chi into ai intersection bj. Here you can observe I have defined my summation from I is equal to 1 to m and summation j is equal to 1 to n. Outside that point, your simple functions will vanishes. So if I consider I is equal to 0 to m and j is equal to 0 to n, your alpha naught and beta naught will be 0. Correct? Now this ai intersection bj is a collection of set obtained by taking all the intersection. This is intersection. So this intersection of two sets forms a finite set which will be disjoint collection of measurable sets. Okay. Now just I am taking integral to my a phi plus b xi. If I take integral over a phi plus b xi, what I will get summation I is equal to 0 to m, summation j is equal to 0 to n. This is something like a constant. A alpha I plus b beta j. So if I apply integral to this characteristic function, what I will get? I will get measure of ai intersection bj. I have explained this in the previous session also. Okay. So now I can write this as summation I is equal to 0 to m, summation j is equal to 0 to n, a alpha I into measure of ai intersection bj plus summation I is equal to 0 to m, summation j is equal to 0 to n, b okay, kindly correct these things in your notes. B beta j measure of ai intersection bj. So if you observe this summation j is equal to 0 to n is applied only for this bj. So what I have done, I have taken summation I is equal to 0 to m a alpha I as it is, measure of ai intersection. I can write using countable additivity property, union j is equal to 0 to n bj. Similarly, here this I is equal to 0 to m is applicable only for this ai. So I can write that as b into beta j measure of union I is equal to 0 to m ai intersection bj. Since a is finite value, I can take out a into summation I is equal to 0 to m alpha I measure of ai. How I can write this as, I will write it here, you can observe, union j is equal to 0 to n bj. I can express this as, if I consider two sets, it will be b0 plus b1, correct? I can write this as summation I is equal to 0 to 1 b0 since union of all subsets of E is a measurable set, sorry, this is bj, I can write this is equal to E. Okay, so now observe here, measure of ai intersection E is nothing but measure of ai. So similarly, I can consider this part as E. So E intersection bj is measure of bj. Okay. So now what you will get? A phi integral a phi plus b xi is equal to a as it is. This is nothing but, using your previous theorem, you can write this as integral phi, and this is nothing but integral xi. So we have proved the first part of the theorem. So now in order to prove the second part, if you put a is equal to 1 and b is equal to -1 in your a, what you will get? You will get integral phi minus integral xi is equal to integral phi minus xi, correct? So since what they have given phi is greater than or equal to xi. So phi is greater than or equal to xi means phi minus xi is greater than or equal to 0 almost everywhere. From that you can write integral phi minus xi is greater than or equal to 0 almost everywhere. So you can express this as integral phi minus integral xi greater than or equal to 0. So from this you can directly write integral phi is greater than or equal to integral xi. The next theorem is a bounded function f defined on a measurable set E of finite measure is Lebesgue integrable if and only if f is measurable. This is your statement. So we know that from the definition of Lebesgue integral of a bounded function, you can write this. That means your lower Lebesgue integral is equal to your upper Lebesgue integral. Those two will be equal to the complete integral, correct? So from that I can write like this. So what I have to prove, I have considered f is a Lebesgue integrable. Now I have to prove that f is measurable. That means I have to prove this is equal to this function f. Okay. So to prove that, I have considered two simple functions phi and xi. Since f is bounded function and phi and xi are my simple functions, I can write f of x is bounded between phi n of x and xi n of x. And this satisfies these two inequalities. So if I add some number to this, I will get strictly less than. Okay, if I subtract some number from this, I will get strictly greater than. So I can say that since I is a complete integral, if you add some quantity to your I, this xi n of x will be less than. So if you subtract some quantity to your supremum, that will be greater than. Okay, so from these two, if you subtract these two, you will get integral xi n of x dx minus integral phi n of x dx. I gets cancelled, so you will get 1 over n. You will actually get 2 by 2n. So if you divide 2 by 2, you will get 1 over n. I will call this as inequality 1. Okay. So now what I have done is, I have defined a function xi star is equal to infimum of xi n and phi star is equal to supremum of phi n. Why? Because this is for one interval. Okay, I have to take supremum of phi n and infimum of xi n, and I have chosen that supremum of phi n as phi star and infimum of xi n as xi star. So if I prove this phi star is equal to psi star is equal to f, then that means f is measurable. Okay, for that what I have done is, I have defined a set, okay, such that, okay, before that, since phi n and xi n are measurable, correct, those two are measurable sets. From that, if you take supremum of all phi n and infimum of all xi n's, that will be also measurable. Since I have defined infimum of xi n as xi star, if this is measurable, obviously xi star is measurable, and if phi n is measurable, supremum of phi n will be measurable. From that you can conclude xi star is measurable. So from that I can define f is less than or equal to xi star, sorry, f is greater than or equal to xi star and less than or equal to xi star. Okay, now I have considered these sets. One is delta is equal to x such that phi star of x is less than xi star of x. Delta r is equal to x from phi star of x less than xi star of x minus 1 over r, and delta r comma n is equal to x from phi n of x is less than xi n of x minus 1 over r. What I have done is, I have chosen set for all these measurable sets. Okay, if I prove these three things, then I can conclude that phi star is equal to xi star is equal to f. Now from this defined set, you can easily say that this delta is nothing but union of r is equal to 1 to infinity delta r. Okay, observe these two. So since delta r comma n is phi n of x less than xi n of x minus 1 over r, and this phi n of x and xi n of x are measurables, delta r is phi star of x less than xi star of x minus 1 over r. This phi star of x is nothing but supremum of phi n, and xi star of x is nothing but infimum of xi n. So from that you can say this delta r contained in this set, correct? So these two conditions are obvious. You need not to prove that. From looking at set itself, you can conclude that. The next thing is measure of delta r comma n is less than r by n. So to prove this, what I have done is I have taken a contradiction part. I have assumed the things in contradiction way. That means measure of delta r comma n is greater than or equal to r by n. So let's see what we will get if you take in a contradiction way. We should get somewhere contradictory thing, right? Let's check that way we will get. So I can write this as integral over delta r comma n xi n of x dx minus integral over delta r comma n phi n of x into dx is equal to integral over delta r comma n xi n of x minus phi n of x into dx. This phi n of x minus xi n of x minus phi n of x, from this you can observe what I have done is 1 over r is less than xi n of x minus phi n of x. That means, can you write xi n of x minus phi n of x is greater than 1 over r? So, this thing is greater than 1 over r. Integral del r comma n dx is nothing but measure of delta r comma n. So, measure of delta r comma n I have written here. From this assumption, I can write 1 over r as it is. This measure of delta r comma n as r by n. So this r and r gets cancelled. So obviously this whole term will be greater than or equal to 1 over n. So if you observe this with your inequality 1, you can say that there exists a contradiction to your inequality 1. This inequality is inequality 1 is true from all the basic definitions, correct? So we are getting contradiction to the definition itself. That means what we have assumed is wrong, and measure of delta r comma n will be always less than r over n. So for if n is arbitrary, what you will get, measure of delta r comma n will be less than 0. So if this is less than 0 means you can say that measure of delta r is, for any arbitrary means since measure will not be, that is length or measurement will never be negative, what I will do, I will say this is equal to 0. I will choose n value like that only. So from this I can say measure of delta r is 0. Since this delta r is subset of delta r comma n, and this delta r, sum of delta r's will be equal to delta, I can write measure of delta is equal to 0. Now I can write phi n of x plus r by n is greater than or equal to xi n of x, and n is arbitrary. So if I choose n as infinity, 1 over infinity is 0. So I will get phi star of x is greater than or equal to xi star of x almost everywhere. In other words, from the definition of almost everywhere, from almost everywhere definition, what I can say, the set of all those points for which the property does not hold have outer measure 0, and hence measure is 0, correct? That means if I consider these as my properties, so these properties should not hold. That means I can say phi star of x is greater than or equal to xi star of x. Since I am getting measure of delta is equal to 0, if I take measure to this, so what we are getting measure of delta is equal to 0, correct? From the definition of almost everywhere, I can write phi star of x is greater than or equal to xi star of x. Why? Because from the definition, what we have from definition, if the set of all points for which the property does not hold, you will get measure of that set as 0. That means this property is not holding. So from that I can write phi star of x is greater than or equal to xi star of x almost everywhere. But we know that infimum will always be less than supremum. Correct? So this is obvious that phi star of x will be less than or equal to xi star. So from these two, what you can write, phi star of x is equal to xi star of x is equal to f almost everywhere. This is what we wanted to get, right? Since each of the function phi star and xi star is measurable, I can say my f is also measurable. There is one more part we have to prove. What is that? I have to consider f is measurable and I should show that it is a Lebesgue integrable. Correct? For that, what I have done is I have assumed f is measurable function, and since f is bounded, I can write f is bounded between minus m and plus m. Okay. So from that you can define a set with 2n equal parts. So I have defined a set. This is my lower bound and this is my upper bound. Okay, my k is varying from minus n to n. So this is the set ek. Since ek's are measurable and disjoint set, I can express ek as e is equal to union k is equal to minus n to n ek. Okay, so from countable additivity property, I can write this as measure of e is equal to summation k is equal to minus n to n measure of ek. So now what I have done is I have taken two simple functions. One is xi n of x and another is phi n of x, and I have defined that simple function using this set. So what I can do for psi n of x is actually what it is a infimum, correct? So for infimum, m by n summation k is equal to minus n to n k into chi ek of x. Similarly, phi n of x as m by n summation k is equal to minus n to n k minus 1 into chi ek of x. So since f of x is bounded function, my f of x is satisfying this condition also. Okay. From that, what I can do is I have taken infimum of all these terms. So I have defined that as infimum xi is greater than or equal to f integral e xi of x dx. This will be less than or equal to, this is a complete integral. So obviously complete integral part will be greater than one such part. So these two will be equal to m over n summation k is equal to minus n to n k into measure of ek. Similarly for phi I have taken supremum. So this is one part will be, in the case of supremum, it will be greater than complete integral part. So this will be equal to m by n summation k is equal to minus n to n k minus 1 measure of ek. Since I have taken integral for this also, we know that integral chi ek of x dx is nothing but measure of ek. Right? So similarly, this is also measure of ek. From these two I can write, that is if I call this as 2 and 3, 2 minus 3 is infimum xi is greater than or equal to f integral over e xi of x dx minus supremum phi is less than or equal to f integral over e phi of x dx. These two will be less than or equal to m over n k minus of k minus 1. So kk gets cancelled, minus into minus is plus, you will get measure of ek. So k summation k is equal to minus into n, measure of ek is nothing but measure of e. That means you can write this is a bounded between 0, so f is Lebesgue integrable on e. Now I will tell how you can define these two things. Okay. You can define upper Lebesgue integral as L denotes Lebesgue integral over e f of x dx. I have denoted bar on the upper limit side, that means upper Lebesgue integrable. Similarly, lower Lebesgue integral as L into integral over e lower bar f of x dx. So what we know that is f of x is our bounded function. From that, since f is bounded function, of course there exist real numbers alpha and beta. How this alpha and beta will be? Alpha is equal to infimum of f of x such that this x belongs to e, and beta will be supremum of f of x such that x belongs to e. Okay, these two are constant functions, or I can call it as simple functions. From these two I can write f of x is bounded between alpha and beta. Now I will consider two sets such that L of f is equal to phi, where this phi is simple function defined on e. Okay, and the phi will be less than or equal to f. That means phi belongs to the set L of f, and this alpha is one of the point in phi. So I can write phi is less than or equal to f of x less than or equal to beta. Okay. So this implies integral over f is less than or equal to integral beta over e. That is nothing but beta into measure of e. Okay. Therefore, the set integral over e phi such that phi belongs to L of f is a non-empty set, non-empty subset of e, and alpha is a member of it, member of this set, and of course it has a upper bound. Upper bound is nothing but beta measure of e. This is upper bound in R. Therefore, I can write supremum phi is less than or equal to f integral over e phi. Okay. Similarly, if I define a set for xi, what you will get? This phi is less than or equal to f of x less than or equal to xi of x, and you can write that integral xi is greater than or equal to, you will define for alpha, I will write it here, integral over xi is greater than or equal to integral over e alpha. That means you will get xi is greater than or equal to alpha into measure of e. What does it mean? Measure of e, alpha measure of e will be lower bound for your xi, and you can express that as infimum of xi greater than or equal to f integral over e xi. infimum xi greater than or equal to f integral over e xi. This is in the case of lower bound and this is in the case of upper bound. Using these two things, I have defined integral over e xi n of x dx will be greater than or equal to infimum xi greater than f integral over e xi of x dx, and integral over e phi n of x dx will be less than or equal to supremum of phi less than or equal to f integral over e phi of x dx. I hope this thing is clear now. The next topic is comparison of Lebesgue and Riemann integrable. We have to compare those two sets, for that those two functions. So for that we have a theorem, those two integrables. The theorem statement is, let f be a bounded function defined on closed interval a comma b. If this f is Riemann integrable over ab, then I have to prove f is Lebesgue integrable also. And Riemann integrable of a to b f of x dx is equal to integral over a to b f of x dx. These two things I have to prove. So what I have taken is, since f is Riemann integrable over closed interval a comma b, from the definition of Riemann integrable, I can write this, correct? So lower bound equal to upper bound equal to Riemann integrable of the function. Here this xi1 of x is and phi1 of x are simple functions or step functions on closed interval a comma b. Why I have called this as a step function is, if I choose summation I is equal to 1 to n phi I, if phi is simple function, then each function I can call that as a step function, okay? And each step function is also a simple function. So from that I can write every step function is a simple function. So this is a simple function, complete simple function, and this is one step function. Okay, if I take supremum, so obviously this whole thing will be greater than or equal to one step function, and if I take infimum, this whole thing will be less than or equal to one step function, correct? So from that I can write your Riemann integrable a to b f of x dx will be less than or equal to this supremum phi is less than or equal to f integral over a to b phi of x dx. Why? Because you are defining your Riemann integrable for step function, and here you are considering simple function. That means